Welcome everybody to our discussion of Riemann-Stieltjes integration. And so before we get started, let's talk about a couple of assumptions that will kind of be holding through all of our discussions about Riemann-Stieltjes integration. So the first one is that we're going to have a closed interval AB on the real number line, and so that closed interval is going to be compact. And just a little bit of a reminder from the Heine-Borel theorem that this is just equivalent to being closed and bounded. So just kind of throw in a little refresher from the past there. So our closed interval AB is going to be compact. And the second assumption that we'll make is that all functions are going to be assumed to be bounded on AB. So we're not going to let anything run off to infinity. It's going to be defined on those intervals, and everything is going to be bounded. So one of the workhorses in our discussions is going to be that of a partition of our interval. So what we mean by a partition of our closed interval AB is just a finite set of points, x0, which is the left endpoint, x1, x2, all the way up to x sub n being the right endpoint. So it's a strictly increasing sequence in that interval. The first value is going to be the left endpoint. The last value is going to be the right endpoint of our interval. And we'll say that the norm of the partition is going to be the length, or the largest length of any of those subintervals that we have in there. So the norm of P, if P is going to be our partition, is just the max of x sub k minus x sub k minus 1 for k going from 1 to n. Now, a second partition, if we've got a second partition, we say that that one is finer than P, or is a refinement of P, if we have P as a subset of our new partition Q. So let's see what happens when we start adding points to our partition, how that impacts the norm. So suppose that we've got a partition P of our interval AB, and we take another point Y that's not already an element of P, and we throw that in, and we make a new partition with P union this new point Y, and we call that one Q. Now, what we have is Y is going to be in one of those subintervals. Say that it's going to be in the subinterval x sub L minus 1 all the way up to x sub L. And now we kind of start looking at that, in the length of that interval. Well, if that interval was the longest interval in our collection of subintervals, then we've just divided the largest interval, so that what would happen is that our norm of our new partition Q would have to be strictly smaller than the norm of P. But it could be the case that there's another subinterval that's that length, and so subdividing x sub L minus 1 and x sub L, it really doesn't do anything to affect the norm, and so the max stays the max, and so we have that the norm of Q is equal to the norm of P. So kind of the third case, if we pick x sub L minus x sub L minus 1, and that's not equal to the max, then essentially we've subdivided an interval that doesn't really make any difference. And so what happens there is the norm of Q still remains the norm of P. And so in all of this, what can we say if we make a refinement? It's basically that our norm is going to decrease possibly. So the norm of the refinement, Q, is going to be less than or equal to the norm of P. Now, because for any real other refinement of P, we're just adding a finite number of points. If we throw in the principle of math induction, it means that for any refinement Q of partition P, that we've got the norm of Q being less than or equal to the norm of P. Now let's talk about our functions and Riemann-Stilljust sums. So if we take two functions, f and alpha, we let those be functions on our closed interval AB. We let P be a partition of AB, and then what we're going to do is define delta alpha sub k being the difference in alpha between the left endpoint and the right endpoint of each subinterval. So our delta alpha sub k is going to be alpha x sub k minus alpha of x sub k minus 1. Now, for each subinterval, we can go through and pick representative t's, t sub k for in each subinterval, x sub k minus 1 to x sub k. And from that, we can form a sum. So our sum S on the partition P of f with respect to alpha is going to be the sum from k goes from 1 to n of f t sub k delta alpha sub k. And a sum of this form is what we will call a RiemannStillJustSum. And kind of one thing to note in all of this is that if we take the special case that alpha of x is just x, so we just take alpha of x to be the identity function, that any RiemannStillJustSum is really nothing more than our plain old Riemann sum from Riemann integration back in calculus that we're familiar with. And so what this means is we are doing a slightly more general theory in that Riemann integration is just going to be a special case of Riemann-Stilljust integration. And so now let's actually look at what it means to have a Riemann-Stilljust integrable. So again, let f and alpha be functions on our closed interval AB. We say that f is going to be Riemann integrable with respect to alpha on the closed interval AB, or sometimes we say that f is Riemann-Stilljust integrable with respect to alpha on AB. And we denote that by this little script r of alpha notation. So what that means to be Riemann-Stilljust integrable on A with respect to alpha is that there's a real number A such that for any epsilon greater than 0, there exists a partition P sub epsilon of AB such that if we take any partition P that's finer than P sub epsilon, and for any choice of points that we want to make, so for any possible Riemann-Stilljust-sum that we could take, if we look at the difference between that sum and our real number A, then that distance is going to be less than epsilon. And so when such a number exists, it is uniquely determined, so not a big surprise. Why would that be true? Well, kind of you're looking at a standard uniqueness thing talking about distances, so we'll leave that proof to the viewer. But what we will do is denote this real number A by the integral from A to B of f d alpha, or sometimes you might see it written as the integral from A to B of f of x d alpha of x. And again, just to kind of reiterate the point again, that if we take alpha of x to be x, then this is exactly the same definition that we have for our usual notion of Riemann integration. So at this point, it's probably good in seeing this notation to issue a little bit of a word of warning that when we had this notation, the integral from a to b of f d alpha, remember that we made absolutely no assumption that alpha was going to be differentiable in any way. We write the d alpha, but all we really know is that alpha is going to be some bounded function on our closed interval AB. So it's one thing to be careful of when you're seeing this d alpha is to make the leap to the assumption, oh, alpha is going to be differentiable. Now we'll deal with that case later, and we'll kind of see how that ends up reducing to something that we're familiar with. But initially, we don't have that assumption that alpha is going to be differentiable, and so just kind of be careful in your mindset of thinking, to get away from alpha being some kind of differentiable function. In that case, we have that, and in general, we get a lot of our applications in the cases where alpha is not going to be differentiable necessarily, or at least differentiable in a finite number of spots. So that to kind of come up later. But at this point, after that word of warning, kind of a reasonable question that you should ask or be thinking about at this point is, all right, so when is this integral actually going to exist? So kind of looking at the most trivial case that we can possibly come up with, what if alpha of x is constant? Then we really see that we really do get something trivial in that if we take any partition of AB, then delta alpha sub k, just being alpha x sub k minus alpha x sub k minus 1, is going to be 0 for all of our x's. So all of our delta alpha sub k's are going to be 0. So if we have any bounded function f, then for whatever RiemannStillJustSum that we take for any selection of t values, we're still going to get 0. And so kind of the absolute most trivial case we can come up with when alpha is constant is that the integral from a to b of f d alpha is just 0. So probably the next most trivial case that we have is just alpha being a step function. So you're constant for part of the interval, then you take one step, and you're constant for the remainder of the interval. And so where this comes in is actually the content of theorem 7.9 in our reference, is that if we're given a c in between a and b, then we can define the step function to just be some real number at c. And then for anything to the left of c, it's the same as the function value at the left endpoint, alpha of a. And anything to the right of c is going to be the same as the function value at the right endpoint, alpha of b. And so kind of the graph of that thing looks something similar to what we have here, that we're just constant to the left of c, we take a step at c, then we're constant to the right of c, and we've got some alpha of c defined somewhere in that interval. We don't really care too much necessarily what it is. So if we let f be defined on our closed interval AB, and we make the condition that either f or alpha is going to be continuous from the left at c, and at least one of them is going to be continuous from the right at c, then we know that f is going to be Riemann-Stieltjes integrable with respect to alpha on our closed interval AB. And in fact, that integral is going to look like the integral from a to b of f d alpha is going to be f of c times alpha of c plus minus alpha of c minus. Now, what is the alpha of c plus? It's the limit as x approaches c from the right of alpha, and alpha of c minus is just going to be the limit as x approaches c from the left of alpha. So let's look at the proof of that theorem. So to start off, let P be a partition of AB, and if we're in the case when C is not necessarily a point of P, then we can actually pass to a just finer partition, P union C, so that without loss of generality, we can assume that C is going to be an element of our partition. So if we look at the Riemann-StillJustSum over this particular partition, then we've got S of P of alpha being the sum from k from 1 to n of f of t sub k delta alpha sub k. Well, let's suppose that C is actually going to be in our interval x sub k minus 1, C less than x sub k, x sub L plus 1. And so what that means is that the only time that we're going to have a non-zero value in that interval is when we hit, in our sum, is when we hit k being L or k being L plus 1. And so our entire sum just reduces to f of t sub L times alpha sub c minus alpha of x sub L minus 1 plus f of t sub L plus 1 times alpha x sub L minus alpha of c. Now, we are thinking that our target is actually going to be f of c times the limit from the right at c minus the limit from the left at c. And so let's actually take a look at the difference between what we have in our sum and what we think our target is. So let's call that difference capital delta. So capital delta equal to our sum, our RiemannStillJustSum, minus what we think our target is. And so if we do a little bit of rearranging, we get an expression here where we're grouping together the f of t sub L minus f of t sub L plus 1. We're grouping together the f of c minus f of t sub L. And then we're grouping together the f of t sub L plus 1 minus f of c. Now, when we do that, what we've actually done in this case is, since our values are just constant to the left, then we can replace alpha of x sub l minus 1 with the limit as alpha approaches c from the left, and alpha of x sub l plus 1 with the limit of alpha approaches c from the right. So then we're going to perform the kind of standard add something, subtract something trick. And so in our expression, we're going to subtract on f of c, and add on f of c. Now, when we do that, do some rearranging, what we find is that our delta is going to be equal to the quantity f of t sub l minus f of c times the quantity alpha of c minus the limit as alpha approaches c from the left, and plus the quantity f of t sub l plus 1 minus f of c times the difference of the limit from the right minus alpha of c. So that if we take the absolute value of that difference, so if we take the absolute value of delta, then we're going to apply the triangle inequality. And so the absolute value of delta is going to be less than or equal to the absolute value of f of t minus f of t sub l minus f of c times alpha of c minus the limit as alpha approaches c from the left, plus f of t sub l plus 1 minus f of c times the difference of the limit as alpha approaches c from the right and alpha of c. So if we let epsilon be any number greater than 0, then if we're assuming that f is continuous from the left at c, then there's going to be a delta such that the absolute value of x minus c less delta means that f of x minus f of c is going to be less than epsilon over m. And likewise, if alpha is continuous from the right at c, then alpha of c, the limit as alpha approaches c from the right, is just going to be alpha of c. And now what was that m? That m was going to be the maximum of alpha of c, the limit of alpha approaches c from the right minus alpha of c, and alpha of c minus the limit as alpha approaches c from the left. So m is going to be the maximum of those two differences that we have in our alphas in our expression for delta. So then if we choose our partition p sub epsilon with the norm of p sub epsilon less than delta, and then for any t in our interval x sub t minus x sub l minus 1 to c, we've got that the absolute value of delta is going to be less than epsilon over m times the difference in alpha of c and the limit as alpha approaches c from the left, plus the absolute value of f of t plus t of l plus 1 minus f of c times 0, because we assumed that alpha was going to be continuous from the right there. And so by the value that we chose for m, that's going to be less than or equal to epsilon over m times m, which just gives us epsilon. Now, if we kind of do the same thing, if we assume that f is continuous from the right at c, then there exists a delta greater than 0. Same thing, same thing's going to apply. But then if we assume that alpha is continuous from the left at c, then what happens, something similar in that if we have the absolute value less than absolute value of delta is going to be less than or equal to the absolute value of f of t sub l minus f of c times 0, because we're assuming continuity of alpha from the left at that point, plus epsilon over m times the difference of the limit as alpha approaches from the right minus alpha of c, but that's going to be less than or equal to epsilon over m times m to give us epsilon again. And so that takes care of the proof. As long as one of those functions is going to be continuous from the left or right at c, then our result holds. So we really don't care too much necessarily what the value of alpha is at c. We just end up with this expression where our integral from a to b of f d alpha is going to be f of c times the limit as alpha approaches c from the right minus the limit of alpha approaches c from the left. And so kind of a nice part about the Riemann-Stieltjes integration is that we're actually able to evaluate the function at a point when we choose the appropriate alpha.